Welcome to part 3 for the area and distance problems involving the area underneath a curve. This one will now here be based on the distance problem. So this is finding this distance traveled by an object during a time period if the velocity of the object is always known. And if the velocity remains constant, we have distance is equal to velocity times time. That's, of course, an assumption that we would have to make based upon that. For this third example, we suppose the odometer on your car is broken and that you want to estimate the distance driven over a 30-second time interval. You take speedometer readings every 5 seconds and record them in the table. And we want the total distance traveled. So we have time going from 0 to 30 and each of the velocities. But we're going to convert these velocities into feet per second. So doing that uses the computation of 1 mile per hour is equal to 5,280 divided by 3,600. This is feet per second. So to do that, this would be 25 for 0, 31 for 5, 35 for 10, 43 for 15, 47 for 20, 45 for 25, and 41 for 30. So for the beginning values of this distance, based on the left endpoints, this will be 25 times the distance of 5 seconds within each interval, plus 31 times 5, plus 35 times 5, plus 43 times 5, plus 47 times 5, plus 45 times 5. And that gives us 1,130 feet as our underestimate. For our overestimate based on the right endpoints, this would be 31 times 5, plus 35 times 5, plus 43 times 5. That's divided by 3, I know. 43 times 5, plus 47 times 5, plus 45 times 5, plus 41 times 5. That estimate is 1,210 feet. So the true area with distance involved in this is between those two values. So the formal distance problem is, in general, suppose an object moves with velocity v is equal to f of t, where t is between a and b inclusive, f of t is greater than or equal to 0. Take velocity readings at times t sub 0 through t sub n, so the velocity is approximately constant each subinterval. As long as these are evenly spaced, the interval is delta t is equal to b minus a divided by n. And this limit as n approaches infinity of the sum of I is equal to 1 to n of f of t sub I minus 1 times delta t should be the same as the limit as n approaches infinity of the sum from I is 1 to n of f of t sub I times delta t. So this is based upon those endpoints. So this is the right endpoints and the left. Excuse me, I just messed that up. This is supposed to be the left and the right. Left endpoints, right endpoints. So with that being said, example 4, we have the graph of the velocity of a braking car is shown. We want to use this graph and a midpoint Raymond sum. Raymond sum is just these calculations we've been doing, just a special name attached to it, with 6 equal subintervals to estimate the distance traveled in feet by the car while the brakes are applied. So those pictures for this, since we are using 6 of these, is going to look something such as this. Just to give you a visual guesstimate of each of these sizes of the rectangles. And that one's actually not drawn as a midpoint. Excuse me. There we go, that's better. Okay, so this would be M sub 6. So from what we have here, this is going to be, since this has a rectangle width of 1 times the velocity at 1/2 plus 1 times the velocity at 1.5 plus 1 times the velocity at 2.5 plus 1 times the velocity at 3.5 plus 1 times the velocity at 4.5 plus 1 times the velocity at 5.5. So, guesstimating these values, this is 1 times 42.75 plus 1 times 30 plus 1 times 21 plus 1 times 13.5 plus 1 times 7.5 plus 1 times 3. And that guesstimate is about 117.75 feet. And then finally, one last example. Using the right endpoints to find the expression for the area under the graph of f as a limit, we don't want to evaluate it. This would be f of x is equal to x squared plus the square root of 1 plus 2x, with x being between 2 and 4 inclusive. Delta x for this will be 4 minus 2 divided by n, so whatever 2 divided by n is. And to get each of these endpoints, x sub I, this would be 2 plus I times delta x, so 2 plus 2 times I divided by n. So this is the area of the limit as n approaches infinity of these right endpoints, R sub n. So the limit as n approaches infinity of the sum from I is 1 to n of f of x sub I times delta x. So using the fancy schmancy mathy notation, this would be the limit as n approaches infinity of the sum from I is 1 to n of a bunch of mumbo jumbo. 2 plus 2I times I divided by n squared based upon the x squared term in this equation. Just replacing the x and that x squared with what we have here for x sub I, plus doing the same thing now with the square root term. This will be the square root of 1 plus 2 times, replacing the x now, 2 plus 2I divided by n. And we're going to take this whole thing and multiply it by delta x. So 2 divided by n. Let me know if you have any questions or concerns. Thank you.